Okay, welcome back. In this lecture, we are going to look at an important alignment algorithm which is known as local alignment. So, let us get started. Over the last two lectures, we have looked at the definition of sequence alignment, what alignment cost means, what edit distance means, what is alignment score, and also algorithm to compute global alignment. We have also looked at finding approximate occurrences of a pattern in a text. We will continue this discussion. So, let us do a recap of all these alignment methods. First was the edit distance based formulation, where we were computing alignment with minimum edits. So, again assuming you have two input sequences as input, that is sequence A and sequence B, then the alignment of, we are seeking an alignment of A and B with minimum cost. That is, if we assume unit cost model, then we are seeking alignment with minimum number of edit operations. So, in this case, this formulation is useful and it is a reasonable metric. So, edit distance is a reasonable metric to measure relatedness of two sequences A and B. So, given the entire sequence A and the entire sequence B, you will know how well these two sequences are aligning after solving this problem. Then we extended this idea to computing global alignment, and the switch or the change that we made here was that instead of minimizing edit distance, here we assume that we have a scoring matrix and the formulation was defined such that we seek an alignment with maximum alignment score. So, that maximum alignment score we can refer to it as a similarity score as well. And again, this is a reasonable metric to measure relatedness of two sequences A and B. So, based on this idea, so we also looked at dynamic programming techniques and then we solved for approximate occurrences of a pattern. So, this time the change was that we were looking for a region inside the text in which the pattern would align well. So, the way to formulate this question was that is there a substring T double dash of T such that the global alignment score of T double dash and P is exceeding certain threshold. So, that threshold can be given by user, and if that threshold is exceeded, then we want to know whether is there an approximate occurrence of a pattern inside a large text or not. So, you can already see that in this formulation now we are looking for a segment or we are looking for a region inside the text where the pattern aligns. So, that is good. Then for this lecture what we are going to do is we are going to look at the local alignment concept. The key difference between local alignment and the previous alignment versions is following. So, again we are given two sequences A and B. We also have a scoring matrix given to us. What we want to know is the substring alpha and beta of strings A and B respectively, whose global alignment score is maximum over all substrings from A and B. So, over all choices of substrings from A and over all choices of substrings from B, we want to look for substrings alpha and beta whose global alignment score is maximum. And the rationale is that now we want to look for regions inside A. So, given a very long sequence, we want to look for a small region inside A that aligns with a small region inside B. So, this is why it is called local alignment, because we are looking for local similarity between sequence A and sequence B. In this case, for example, we may not expect the sequence A, the entire sequence A to align well to entire sequence B, but maybe there are some local similarity patterns that we want to identify, and that is what this formulation will give us. That is to look for substrings alpha and beta of A and B respectively, whose global alignment score is maximum over all substrings from A and B. Right. So, this is how I can visualize all the alignment problem formulations we have looked so far. So, in the edit distance, the alignment optimization type is based on minimization, right. In the global alignment and thereafter we looked at the optimization problems which involved maximization of the alignment score. In all cases so far we have managed to come up with the order mn algorithm using dynamic programming techniques, and for today's lecture as well we are going to see an order mn algorithm for solving local alignment problem as well. So, one thing that is remarkable is that all these problem formulations are very different from each other, but it always turns out that they are always solvable in order mn time, and the techniques that we are using for solving this problem are very similar to each other. That is, we are always relying on dynamic programming techniques to solve all these problems. So, let us dig deeper into the local alignment concept. So, as a first step let us also look at the history of these alignment algorithms. So, the concept of global alignment came into the picture in 1970 when Needleman and Wunsch, two authors, introduced the global alignment problem. So, when this global alignment problem was introduced, the original algorithm that was proposed to solve that problem was cubic instead of quadratic. So, even though in the lecture we have already seen quadratic algorithm, the original algorithm that was first developed for this problem was cubic in 1970. Subsequently in 1972, David Sankoff published a quadratic time algorithm for computing global alignment that we have also seen in this lecture. In 1981, this concept of local alignment was introduced to find local similarity between sequences. So, this was introduced by two authors, Smith and Waterman. And subsequently when these concepts were mature, in 1985 onwards many practical implementations started coming up which implemented these algorithms and made easier for biologists to use these algorithms. So, some of the popular alignment algorithms and software from those times are FastP, FASTA and BLAST, and subsequently maybe in 1990 onwards I can say that several other methods have developed that are even faster than the original methods that were developed previously. So, these algorithms are using different techniques to achieve faster run times, but that is not the focus of this lecture. The lecture will focus on the local alignment problem introduced by Smith and Waterman. Now, I want to emphasize that these local alignment problems are very important in biological sequence analysis. So, if we look at just one example which is one of the most popular local alignment search method. So, this method basically uses local alignment. If you give it a sequence, it will do a local alignment of that sequence against a very large database of genomes and other repositories. And you can already see based on the citation count that why this tool is so important in modern biology. So, the topic of this lecture is to understand this local alignment problem formulation, and then we will subsequently look at how this problem is solved efficiently. Let me also give you some motivating examples of where local alignment may be useful, right. So, again going back to the problem formulation, remember that this problem formulation is allowing us to look for local similarity between sequences A and B. So far we have in the previous concepts we have looked for global similarity among sequences A and B. So, for example, we know how to check similarity between entire sequence A and entire sequence B, whereas this formulation will allow us to look for local regions in A and local regions in B that match well. So, again the problem formulation is that finding substrings alpha and beta of A and B respectively whose global alignment score is maximum over all substrings of A and B. And when I say over all substrings of A and B, this also includes empty substrings. Okay. So let us look at some of the motivating examples for why you may want to use local alignment algorithms. So let us consider the first easiest example, where let us say we want to compare human and camel hemoglobin protein sequences. Now you can expect that the hemoglobin is highly conserved sequence. So it serves an important function in humans as well as camels, and there in these cases we expect that the entire sequence will be highly conserved. So for example, if you look at the hemoglobin subunit alpha protein sequence, or if you look at hemoglobin subunit beta sequence, you can see that the sequences are similar from end to end. So similarly in the second case, the sequences show us pattern of similarity from begin to end. Now in this case we do not need local alignment. This is an example where global alignment already would give us the relationship between these two sequences. So we would know what sequences or what characters match and where are the mutations happening, right. So this, for this example, global alignment serves the purpose. But what about when we look for distant proteins? For example, maybe proteins in very distant species like human and plants. So this is another example in which I am showing you conserved protein domains in PARPs and PARP like proteins of human and Arabidopsis plant. So what you can see is that, so here I am showing you the protein sequences and I am also showing you these domain structures. So each block is a domain structure. So these domains are basically subunits of the protein sequences. What you can see is that on the left are the protein sequences from humans and on the right are the protein sequences from Arabidopsis plant. While these sequences are very dissimilar to each other, like you can already see that the domains are very different from each other, but there is a highly conserved domain which is similar in both sequences. So now when I want to, let us say, compare one sequence from here to one sequence from here, then it does not make sense to use global alignment anymore, because these sequences do not share end to end similarity. This is an example where you would want to use local alignment, where so that you can see the local region of similarity between these two sequences. Let us look at another example. So in this particular example I am comparing two yeast genomes. So yeast genomes are typically of length 13 million bases, but when I am comparing entire genome sequences, again it is very unlikely that the entire genome sequences will share end to end similarity. It is very likely that they will have local regions of similarity between the genome sequences, but end to end similarity is unlikely because of large structural changes and rearrangements. So again when I am comparing complete genome sequences of genomes like yeast, which are very long, so in this case it is 13 million bases, in this case using local alignments would make more sense, because then I can look for local similarity regions between both genome sequences. So on the left I am showing you a dot plot visualization of the alignment. So this is not the standard way. So far we have not looked at so traditional way that we have focused so far is this way of looking at character by character, right. But on the left this is a dot plot, which is another way to visualize alignments. So for example, this particular line segment indicates that this region of the genome starting from some locus to some locus, so this is start locus and this is the end, matches to this region of the genome. So this is a dot plot visualization where it's in a matrix format in some sense, and it's showing you what regions of genome 1 align to what regions of genome 2, and you can already see some local patterns of alignment. So for example, this is showing you a local similarity between this region of the genome to this region of the genome. Similarly, this is again a local similarity pattern that shows a similarity between this region of the genome to this region of the genome too, and so on. So, one can expect multiple such local alignment patterns in such large genome sequences, and this is where getting, if I were to solve a global alignment formulation, then the alignment that I would get may not be biologically meaningful, whereas local alignments would give us more biologically meaningful output of those local conservation patterns between two genome sequences. Here is one last example that I want to show you. In this case, I am comparing chromosome Y sequence of human genome to chromosome Y sequence of chimpanzee genome, and again you can see that they do not share an end to end similarity, because if they had an end to end similarity, then I would see my local alignments along the diagonal, but that is not the case. You can see many local alignments forming up, and again this is a dot plot visualization where each alignment, each segment in this plot is showing me the local similarity between regions of the two genomes. So, again in this case chromosome Y length is close to 60 million bases, and because this is very long and you can expect many rearrangements and structural changes to happen, this is where end to end global alignment will not work. Local alignments instead can give us the local similarity patterns between both sequences, which will tell us what regions are conserved between chimpanzee and human genomes. Okay. So, I hope now you are convinced why local alignment is such an important topic in biological sequence analysis. So, let us dive into what algorithms can we use to solve this problem efficiently, because our inputs can be very large in general. So, we need efficient algorithms to solve this problem. Okay. So, coming back to the problem definition, again remember that we have two input sequences A and B. The length of sequence A is m and length of sequence B is n. We are given a scoring matrix. The question is to look for substrings alpha and beta in A and B whose global alignment score is maximum. So, these alpha and beta should give you a very high alignment score if you align these two alpha and beta strings, and you are welcome to choose any substring from A and any substring from B. So, this optimization has to select appropriate alpha and appropriate beta from both strings A and B respectively. So, once that let us use V star to denote the global alignment score between the selected substrings alpha and beta. Now, how would you solve this problem? Well, one brute force way to solve this problem may be to look at all possible substrings of sequence A and all possible substrings of sequence B one by one. So, for example, we already have m square possible sequences in sequence A, we have order n square substrings in sequence B, and if I take each of these sequence pairs and I do a global alignment, that also requires further order mn time, because each global alignment will require order mn time. So, if you multiply all these, it turns out that the brute force algorithm would take order m cube times n cube time. This is when I am considering each and every substring of A and each and every substring of B and checking whether their alignment score, and I will pick the pair which gives me the maximum score in the end. So, this naive algorithm is not going to work because m cube times n cube is extremely slow. The question is, can we do better? Well, let us see. So here is one trick that we are going to use. Let us consider a restricted problem. So for this restricted problem, again assume that you have two sequences A and B. Now in this restricted problem, the problem statement is as following. So we are given two offsets I and j. So these I and j are given as input, and what I have to do is I have to find a suffix alpha of A1 to I and suffix beta of B1 to j, whose global alignment score is maximum over all pairs of suffixes of A1 to I and overall pair or overall suffixes from B1 to j. For example, let us say we consider this example where my sequence A is P Q R A X A B C S T V Q, and let us say my sequence B is just X Y A X B A C S L L. So these are just two examples that I want to show you. So let us say that in this problem formulation I and j were given to me as these coordinates. Now the formulation is asking to find the appropriate suffix of this string. So find a suffix of this string and similarly find a suffix of this string such that the global alignment score between both suffixes is maximum. So for example, I can pick any of these, any suffix of this string, I can pick a suffix of this string, and then I have to check what is the global alignment score between those two strings. So for example, is if I pick this suffix and from second string I pick YAX BACS, then I have to compute global alignment and check what is the global alignment score given by these two suffixes. Similarly, I can make other choices. I can pick suffix ABCS, or I can pick from second string I can pick BACS. So in this case I will have to check ABCS and BACS, and I will have to check what is the global alignment score of these two strings. And as you can see, basically we can pick any suffix ending at I and any suffix ending at j. So we have to make an optimal choice which maximizes the global alignment score between them. So for this particular example, it turns out that the suffix which maximizes the global alignment score is AXABCS from sequence 1 and AXBACS from sequence 2. So if you try any other suffix, it will give you a less global alignment score. So for these two suffixes, the global alignment will look like this, and assuming this scoring system where you reward each match as 2, each mismatch as -2 and each space character or each dash character as -1. So under this scoring system you can already see that this global alignment has score 8, because you have a mismatch, you have a match, you have again a match, you have a dash character. So I will subtract 1, then you have a match, then you have a dash character, and then you have a match, and again then you have a match. So this adds up to 8, and what I am saying is that for this particular example the optimal choice for the suffix is alpha and beta, that is AXABCS and AXBACS. So if you pick any other suffixes of these two strings, so if you pick any other suffix of these two strings, then you will achieve a score lower than 8. So therefore this choice is optimal for this value of I and j. Now why are we discussing this restricted problem? How is this connected to our local alignment problem? Well, there is a connection, and the connection is following, that if I denote the solution to this problem, that is the global alignment score that I achieve between alpha and beta, if I denote it as v small vij, then it turns out that the local alignment value of the local alignment, that is the score of the local alignment, is equal to the maximum over all vij values. So, if I look at maximum of vij over all I ranging from 1 to m and all j ranging from 1 to n, then all such vij values, maximizing them over all I and all j's will give me the local alignment score. Why is that the case? Well, the observation is simple, because if you look at the local alignment property, so we are looking for substrings alpha and beta of A and B here, whose alignment score is maximum. Now, these alpha and beta will end at sub positions, right. So, suppose alpha ends at position P in A and let us say beta ends at position Q in B. So, in this case my local alignment score would be equivalent to small v p comma q, because if I look at v p comma q, it would have chosen these alpha and beta as its suffixes, right, because these are the substrings which are giving me the maximum local alignment score, and naturally these would have been considered by one of these values. So, depending on where these alpha and beta strings are ending, it would have been considered in that for that particular value of I and j. So, therefore, if I can solve this restricted problem efficiently, I can solve my local alignment problem efficiently as well, because of this relationship. So, let us understand how we can solve this restricted problem more efficiently. In other words, I need a efficient strategy to calculate these Vij values, and if I know all the Vij values, then I can do a simple scan of all the Vij values and compute my local alignment score as well. So, let us look at how can we solve for these Vij's. Now, again remember that Vij is equivalent to maximum global alignment score between a suffix of a1 to I and a suffix of b1 to j over all pairs of suffixes. So, for example, while computing Vij, I have to consider all possible suffixes of b1 to j, and I have to consider all possible suffixes of a1 to I, and depending on which one gives me the maximum alignment score, I will define my Vij accordingly. Now, again a naive way to compute Vij would be to iterate over all pairs of suffixes, but again then we are going back to our bad algorithm, which will take too much time. So, can we compute these Vij values more smartly? Well, yes, there is a way. So, let us start by asking simpler questions. What would be the value of Vi comma 0? That is, what would be the value of Vi comma 0? In this case, I am asking for a suffix of, so we have to look for a suffix of a1 to I against a suffix of empty string, which means I am trying to align a suffix of a1 to I to a empty string. So, in this case, because if the best choice I can make here is to pick a empty suffix of a1 to I, because then I do not have to delete any characters to align to the empty string, because remember that if I want to consider a non-empty suffix, then I would have to, suppose I consider a non-empty suffix, then I would have to insert dash characters in my alignment, which would give me a negative alignment cost. So, in order to prevent that, what I can do is I can select a empty suffix, that is an empty string, and the cost of aligning empty string to empty string is 0. So that is the score of aligning empty string to empty string is 0 because there is no character that is getting matched or mismatched. So therefore this is equal to 0, that is I can pick a empty suffix of A1 to I and align it to an empty string from B, and aligning two empty strings, the alignment score is obviously 0. I can apply the same logic to V0 comma j as well, that is again I can pick a empty suffix of B1 to j and align two empty strings with alignment score 0, because that is the optimal choice I can make. If I pick a non-empty suffix again, then I would have to give a negative alignment cost. Okay. So these two cases are trivial, we get 0 values for both of these scenarios. What about the general case when I and j both are non-zero? Again as I mentioned that we want to avoid the naive approach of iterating over all pairs of suffixes, because that would be very slow. So a clever approach would be that, similar to our previous algorithms, we will try to establish a recurrence between Vij, Vi minus 1j, Vij minus 1 and Vi minus 1 j minus 1. So this logic is very similar to what we have discussed before, and the same logic applies here as well. That is, using this recursion we will be able to solve these Vij's more efficiently. So what would that recursion be? Well, the recursion follows similar strategy that we have looked so far. That is, we have to look at all the possible ways in which the alignment can end. So because we have A1 to I and we have to pick a suffix of B1 to j that maximizes the alignment score. Now this alignment can end in three possible ways. Either it can end with a match mismatch of two characters from A and B, or it can end with a alignment of ith character of A to a space symbol right. So in this case the alignment ends with a space symbol, or the third possibility is that the alignment ends with the alignment of space symbol to Bj. So these are the only three possibilities in which the alignment of a suffix of A1 to I and a suffix of B1 to j can end. So again, going by the three possibilities, we can give this recursion to compute Vij. That is, if we have already solved for these three values, then in order one time we can solve for Vij as well. There is one small catch that we have to address here, that is, we have to also allow a value 0 in the recursion. The reason is that we can also pick empty suffixes in our choice. So when we are defining Vij, we are also allowed to pick empty suffixes from A1 to I as well as B1 to j. And because we are allowed to pick empty suffixes, we also have a choice of having a alignment score 0. That is, in other words, the local alignment score will never be negative, because we can always pick an empty suffix. If all my possible alignments are negative, then I can always pick an empty suffix such that my score is at least 0. So therefore, in this particular case, my alignment scores in my dynamic programming table will always remain positive. So they will be 0 or more than 0. So now that we have the recursion, the procedure is same as before, that is, we compute the entire DP table either row by row or column by column, and from the DP table we have to look for the maximum value of Vij, because remember that the local alignment score is given by maximum of these Vij values. So, from this, once we have computed the DP table, we have to scan for the maximum value in this table. So, again, so suppose we have computed the entire DP table, we have to scan for the maximum value in the table, and this will give us the location in both strings where the local alignment ends. From here we have to do the trace back, that is we have to trace back our decisions on how we computed this score, and as we move up in our recursion we will have to see what decisions we made in our recursion, that is did we use a diagonal value, or did we use a upper value, or did we use a left value while solving for each element, and depending on the choice we will go up, except that in the global alignment we used to go to all the way to the top left. In case of local alignment we will stop at the cell which is equal to 0, because the value 0 indicates the start of the local alignment. So, in this case you can see that the local alignment starts from here and it ends here. So, this is where the dynamic programming score is 12, and as I move back in my trace back, this is where I will stop, and at this point the score will be 0, because here while computing this value I have an empty suffix which I chose, and then I started growing the suffixes from that point. So, start in summary, compute a DP table, look for the cell with the maximum value, start the trace back from that point and move up until you hit value 0. So, that range in the dynamic programming table will give you the alpha and beta strings that correspond to the local alignment problem. So, these are the alpha and beta substrings of A and B which give the maximum global alignment score for this objective function. I also want to highlight the proof of recursion is very simple, that is if we want to prove that this recursion is correct, then the argument is very simple. So, we can prove that this recursion computes each Vij score correctly. The argument is as following, that for example, if we assume that let alpha and beta be the suffixes of A1 to I and B1 to J, whose global alignment score is maximum. Now, case 1 is that if both alpha and beta are empty, then this case is considered in the recursion, because we have allowed Vij to be 0 in our recursion already. So, this case is being considered. Now, if alpha and beta are non-empty strings, then basically we have to look at all possible ways in which the alignment of alpha and beta ends. And again, going back with our previous arguments, that the alignment can end with only 3 possible ways, that is match mismatch, or alignment of alpha, alignment of AI to a dash character, or alignment of Bj to a dash character. So, these are the only 3 possibilities in which these alignments can end. So, therefore, if you look at all 3 cases, you will end up proving that all these 3 cases have been considered already in the recursion as well. So, the proof is simple in that sense, and we have seen how we can fill the dynamic programming table and solve the trace back to get those alpha and beta strings for the local alignment problem. One small detail that I have to mention here is that typically in practice, when we are solving local alignment problem, we are also looking for multiple regions of high similarity. So, for example, if I am aligning chromosome Y of human to chromosome Y of chimpanzee, there will be several regions of high similarity. In that case, the technique that we have to use is we have to look for multiple cells in the table which have high value. So, for example, we define a threshold and we see that these cells have high value, and then we can individually start trace back from each of these cells, and each of these cells will give us substrings from both genomes. So, this will give me this substring, each of these trace back will give me substrings from both genomes that have high similarity. So, to conclude, we have shown that the local alignment problem can be solved in order mn time using very similar technique that we have seen so far, that is dynamic programming, and compared to the naive algorithm which was order m cube n cube, this is a significant improvement. And I hope you appreciate that all these problems that we have seen so far, they are very different in nature in terms of the how we define them. That is, what are the alignment properties. For example, in local alignment we were looking at substrings of both strings, but in the end we were all able to solve all the problems in order mn time, and that is because of the clever recursion structure that we can see in all these problems. So, the key result is that all these problem variants can be solved in order mn time, starting from eddy distance, global alignment, approximate pattern matching, as well as local alignment. In the next lecture, we are going to study one more detail of these alignment methods, that is the alignment gaps. In that sense, in there we will see that how do we score these alignment gaps. For example, if we have long insertion or long deletion in the genome sequences, how do we define the scoring system so that we get back the alignments that are more biologically real. So, for example, these are mathematical formulations and they can always give some outputs which are not biologically correct. So, we have to be careful in how we define the formulations, and in the next lecture we will see how we can improve these formulations so that those alignment gaps reflect true biology as well. Thank you.